By definition, lambda is an eigenvalue of A if and only if AX equals lambda x has a non-trivial solution. We discovered in the last video that this is the same as saying that A minus lambda times the identity, all this times x equals 0, has a non-trivial solution. But we can make this a bit simpler by using determinants. This is the same by Fatim as saying that A minus lambda I is invertible, and by theorem 4.6, this is the same as saying that the determinant of A minus lambda I is not 0. Why is this helpful? Well, notice that this guy here, this is always a polynomial in lambda. So for instance, if A is equal to A, B, C, D, then the determinant of A minus lambda I is equal to this thing here. When we expand this out using the formula for the determinant, this is A minus lambda D minus lambda minus BC, which is lambda squared minus A plus B times lambda plus AD minus BC. Now you don't have to memorize this formula, or at least this polynomial here. But the important thing to notice is that this is a degree 2 polynomial. Similarly, if A is n by n, then the determinant of A minus lambda I is a polynomial of degree n. We call this polynomial the characteristic polynomial of A, and we call the determinant of A minus lambda I equal to 0 the characteristic equation of A. Now I'm going to go ahead and talk to you about the actual method that we're going to use to find all the eigenvalues and eigenvectors. To help us, I put the definition of the characteristic polynomial and equation up here. Our first step is to compute the characteristic polynomial using determinants. Our second step is to find all the eigenvalues of A, which, by what we know from the earlier in the video, are the solutions to the characteristic equation. And finally, for each eigenvalue lambda, what we're going to do is we're going to find a basis for the eigenspace of lambda, which remember is the null space of A minus lambda I, by solving the system of equations here. Usually when someone asks you to go ahead and actually find the eigenvectors for an eigenvalue, what they actually mean is find a basis for the eigenspace of that eigenvalue. Before going on to an example, I want to point out a theorem! An n by n matrix A has at most n distinct eigenvalues. This is simply because the characteristic polynomial is a polynomial of degree n for an n by n matrix, and by the fundamental theorem of algebra, this has at most n roots. Now, if you're not familiar with the fundamental theorem of algebra, I would encourage you to go to appendix, I think it's appendix D in the book, and everything we will need for this unit is in Appendix D. So now for an example. We're going to find the eigenvalues and eigenvectors of A equals this matrix. Start off by finding, using step 1, the characteristic polynomial. The determinant of A minus lambda I is equal to this determinant here. Using the cofactor expansion, so expanding along the first row, this is equal to minus lambda times 4 minus lambda plus 5 minus 0 minus 2 plus 0, which, when I expand everything out and stuff, I get minus lambda cubed plus 4 lambda squared minus 5 lambda plus 2. For reference, I'm going to call this p of lambda. That's the polynomial here. Our next step now is to solve the polynomial. So we need to find all the eigenvalues. Here I'm going to use something called the rational root test, which should be in your book. The possible rational roots of this polynomial are plus or minus 1 and plus or minus 2. So to get that, because I have a plus or minus 1 here, I can forget about that part. For here, I look at the constant term and say, okay, what are all the factors of 2? What are all the factors of 2? And I have plus or minus each of those factors. So we can do and just go trial and error and test these. So p of 1 equals minus 1 plus 4 minus 5 plus 2, which is 0. And therefore, lambda equals 1 is a root. To find the other roots, we can either do something ad hoc, which is what I'm going to do because I don't want to require you to learn the other methods that you can use, which are polynomial long division, which is in the back of which is in Appendix D of your book, or you can do something like synthetic division, which I don't think is there, but you might have already learned. So therefore, p of lambda is equal to lambda minus 1 times sum a times lambda squared plus b lambda plus c for some numbers a, b, and c. This expands as, after I simplify things, to a times lambda cubed plus b minus a times lambda squared plus c minus b times lambda minus c. Comparing that with p of lambda over here and equating coefficients, we see that a is negative 1, b minus a is equal to 4, and therefore b is equal to 4 minus 1 is equal to 3. And c minus b is equal to minus 5, and therefore c is equal to minus 5 plus 3, which is equal to minus 2, which checks out when we look at equating the 2 here with the minus c here. So, therefore, p of lambda is lambda minus 1 times minus lambda squared minus plus 3 lambda minus 2, which factors as minus lambda minus 1 squared times lambda minus 2. And therefore, the eigenvalues are lambda equals 1 and lambda equals 2. I'm going to box those because that's part of our final answer. To save some space, I'm going to disappear some of what I've already written. Our next step is now to find the eigenvectors. Or more specifically, bases for the eigenspaces. I'm only going to do this for lambda equals 1. The lambda equals 2, 1 is similar. So our first step is to look at what's the matrix. Okay, this is A minus 1 times I, and then putting here, which is going to be this augmented matrix. We can then use Gaussian elimination to get the reduced row echelon form. So this is actually Gauss-Jordan elimination. 1, 0, minus 1, 0, 0, 1, minus 1, 0, 0, 0, 0, 0. Notice that I have a row of zeros on the bottom. If you don't, that means that you did something wrong. Either you did something wrong in the Gaussian elimination, or you did something wrong in finding the eigenvalue. So from this, we get therefore, okay, our free variable is going to be x3. So x3 is t. And from the first equation, we get x1 equals x3 equals t. And from the second equation, we get x2 equals x3 equals t. So therefore, the eigenspace E1 is the set t, 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 the set of all vectors that look like this, such that t is in R. Or in other words, this is the span of the single vector 1, 1, 1. Since there's just one vector here, that means that 1, 1, 1 is a basis for E1. And like I said, lambda equals 2 is similar.